class. This is going to be your lecture on 5.4. 5.4 has the very auspicious title, Fundamental Theorem of Calculus. There's actually several fundamental theorems in mathematics. There's the fundamental theorem of arithmetic, which has to do with prime factorizations being unique. There's the fundamental theorem of algebra, which talks about the number of roots of a polynomial. If you allow complex roots of a polynomial, then you get a number of roots, and I suppose multiplicity, then you get a number of roots equal to the degree of the polynomial. And today we're going to talk about the fundamental theorem of calculus. That's not mem, that's mean. We have a mean value theorem for integrals that we have to talk about first. The reason we're going to talk about this is if we were going to prove the fundamental theorem part 1, we would need to use the mean value theorem for integrals. And I'm actually, when I get there, I'm going to encourage you to read through the proof, but I'm not going to do it on the lecture. I don't think that me saying it out loud gives you any new information. So I'm going to skip the proof on fundamental theorem part 1. The proof on fundamental theorem part 2 is pretty quick, and so I will probably go through that. We'll see how I feel when I get there. So the whole gist of 5.4 is doing integrals by limits of Riemann sums is kind of a pain. And I keep saying that because it really is. I mean, some of them aren't too bad at all, but some of them are just really awful, and who wants to do that every time? And so the fundamental theorem actually gives us another way to do our integrals. And so without any further explanation, let me give you these statements. So the mean value theorem for definite integrals. You can read this on page 330 of your book. So if f is continuous on the interval AB, then at some point C in AB, does it ever bother you that we stick C in between A and B all the time in these? Sometimes it bothers me. I mean, I know it shouldn't, but I was raised on Sesame Street. So in that case, we have f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Remember, this is the average value of f over ab. So what we're saying is, for the mean value theorem, is that the function, if it's continuous, will actually take on its average value somewhere. And if you just draw this out, a few continuous functions on some intervals, you'll see why that has to be so. This continuous is so important here. If f isn't continuous, then we can totally make this, I mean, we could have a function like this. That's integrable from a to b. The average value is going to be somewhere in between there, and of course it doesn't take this on anywhere. So the continuous is important, but that's the idea, is that the function, a continuous function, will take on its average value on any interval. The fundamental theorem part 1, the fundamental theorem of calculus part 1. So the fundamental theorem of calculus part 1 says this. It's real simple. I'm probably going to skip some. I'm going to leave room for hypothesis here because the statement is just so cool. So f prime of x, or I should say the derivative with respect to x, of the integral from a up to x of f of t dt is just little f of x. That's it. The derivative of a definite integral where instead of a b up top I put my variable, and that's the variable. Ooh, that's not supposed to be an equal sign. The derivative with respect to x where the variable is in the top limit of integration, there's no x's anywhere else, is just this function evaluated at x. So now what needs to be true? if f is continuous on AB, no surprise there, where we have a f as an integrand, so we want it to be continuous. Then cap f of x, which is equal to the integral from a up to x. So we're going to define a function in terms of an integral. F of t dt is also continuous. On AB, at least so long as x is between a and b, and it's differentiable. On AB, I almost left enough room, and then we can take its derivative like so. So, like I said, it's really a straightforward thing. There's two kind of proofs in your book. There's an explanation on 331, and the explanation is kind of graphical, and you might prefer that. And then there's a proof on page 333 that involves the mean value theorem for integrals and the limit definition of derivatives, and it's definitely worth a read through. But if you skip it, you're not going to hurt my feelings. It's not fundamental to your understanding of calculus that you be able to prove these things, but that you know how they work. So let's do a couple of examples with this. I'm going to just steal some out of the book here. So an example, we're going to find dy dx for each of these cases. So the first one here is y equals the integral from a up to x of t cubed plus 1 dt. So then dy dx is just equal to x cubed plus 1. That's all we're doing here, is the derivative of the, maybe I'll do a couple extra steps here, is equal to the derivative with respect to x of the integral from a to x of t cubed plus 1 dt. You can see that we're taking the derivative with respect to x. That's the top limit. There's no x's anywhere else. So every place in the integrand that there was a t, I now put an x. That's exactly what the fundamental theorem part 1 says. So that's how I got my x cubed plus 1. B gives us a little bit of interest here. So I'm following example 2 on page 332 if you want to read along in the book. This is the integral from x up to 5 of 3t sine t dt. Before we can use the fundamental theorem on this, we need to write the x as the top limit. So dy dx is equal to d dx of the integral from x to 5, 3t sine t dt. This is the integral, or sorry, the derivative with respect to x of the integral of 5 up to x if I just put a negative on the outside, right? That was in the last section, our properties of integrals. So negative 3t sine t dt, which means that this is negative 3x sine x. Now, if you're wondering why it doesn't matter that this is a 5 and that's an a, keep in mind we're taking derivatives. And if I were to do this using a Riemann sum, that 5 is going to lead itself out to a constant term, so we can ignore it. And the derivative of that would be 0. Got a couple more here. What if y equals the integral from 1 to x squared of cosine t dt? Pardon me a second. All right. I just paused the video so I could get a cough drop. Sorry about that. Let's see. Oh yeah. The integral of 1 to x squared of cosine t dt. So we want to find dy dx here. That's the derivative with respect to x of this integral. So now we've got a little bit of weirdness in that we have an x squared up here. But remember, this whole thing is just our function of x. So this is where the chain rule comes into play. So this is equal to cosine of x squared times the derivative with respect to x of x squared. So that's just 2x cosine x squared. Got one more from that set. Y is the integral from 1 plus 3x squared up to 4 of 1 over 2 plus e to the t dt. So y prime is equal to the derivative with respect to x of this guy, the integral from 1 plus 3x squared up to 4 of 1 over 2 plus e to the t dt. So that's going to be equal to negative, because I've got to flip that up to the top, 1 over 2 plus e to the, plug everything in, 1 plus 3x squared, times the derivative of 1 plus 3x squared, which is 6x. We could clean that up a little, but it's not necessary. So that's the fundamental theorem part 1. If you have a function that's defined in terms of an integral, then the derivative can be computed using the fundamental theorem. Now, the fundamental theorem part 2. So the fundamental theorem of calculus part 2 says, if little f is continuous. By the way, this is the one that everybody loves, because this is the one that says we don't have to use Riemann sums most of the time. On AB, and cap f is an antiderivative of little f. Remember, that means that cap f prime equals little f. It's been a few sections since we talked about antiderivatives. Then the definite integral from a to b of f of x dx can be computed by taking an antiderivative of f at b and subtracting that same antiderivative evaluated at a. So let's prove this. First of all, f is continuous, and so we have the fundamental theorem part 1 tells us that we can define g of x to be equal to the integral from a up to x of f of t dt, and that tells me that g prime of x will be f of x. So that g is an antiderivative of little f. And then from back in, what was that, 4.11, I don't know, near the end of chapter 4, we know that any antiderivative of f can be at most different from another antiderivative by a constant. So we'll let f be an arbitrary, any antiderivative of little f. Then it's going to be some constant plus cap g. It's going to turn out to not matter what the constant is, and that's the idea. So then f of b minus f of a equals g of b plus c minus g of a plus c, same c, so see the c's cancel, so just g of b minus g of a. G of b is the integral from a to b of f of x dx, and g of a is the integral from a to a of f of x dx. But that's 0 because we're integrating from a to a. So you see we have the integral from a to b of little f of x dx is equal to f of b minus f of a, where cap f is any antiderivative of lowercase f. So remember that we can compute area using integrals, but we have to be careful, and I was telling you about net area last time, I think. So this is example 7 on page 338. If I take f of x is sine x between x equals 0 and x equals 2 pi, and I want to find the area under that curve, remember that sine on that interval looks a bit like that. And so if I take the integral from 0 to 2 pi of sine x dx, and the antiderivative of sine is minus cosine x, and then I can evaluate that as when x is 0 and 2 pi, so that's negative cosine of 2 pi minus a negative cosine of 0. That's negative 1 plus 1, that is 0. So it doesn't actually give me the area bounded by the curve. If I wanted to find the area of this shaded region, though, I could say the area is equal to the integral from 0 to pi, that's above the curve, so that's sine x dx, plus the absolute value of the integral from pi to 2 pi of sine x dx. Because when I take that integral, I'm going to get a negative value. And so the total area is the absolute value of each of these pieces summed up. So antiderivative is still minus cosine x. We'll evaluate it when x is 0 and pi and subtract that, plus negative cosine x evaluated between pi and 2 pi. So here is minus cosine of pi minus a negative, so plus a cosine of 0, plus, and then in the absolute values I get negative cosine 2 pi plus cosine pi. So cosine of pi is negative 1, so that's going to be positive 1. Cosine of 0 is 1, so that's going to be another 1, 2 in total, and then plus the absolute value. I gotta make my ones look a little different with those absolute value bars there. So minus cosine of 2 pi is negative 1, plus cosine of pi, that's another negative 1. So that's going to be negative 2 in the absolute value of 4 altogether. I'd like to, do a couple of these problems. I've got you guys doing the odd ones now, so let me just do a couple of the even ones from page 339. Our derivative rules here are going to be handy. Let's start with number 2. It's nice and simple. The integral from negative 1 to 1 of x squared minus 2x plus 3 dx. So your antiderivatives, and again, I know it's been a few weeks since we looked at these. We're going to have x cubed over 3 minus x squared, that would normally be over 2, but we already had a 2, plus 3. And then this evaluation bar is really common with a definite integral. I've used it a couple of times already, but we just say x goes from negative 1 to 1. It allows us to write a step with just our antiderivative, whichever one we want, and then we can write another step where we evaluate it. So that'll be 1/3 minus 1 plus 3. That should have been 3x. The antiderivative of 3 is 3x. That's still a plus 3 there. Minus the same antiderivative with minus 1 plugged in. So that'll be negative 1/3 minus 1 minus 3. These will cancel. That's going to be 6 plus 2/3, right? And 6 plus 2/3, that's going to be 20/3. Let's see. Number 14 has a little something to it. So number 14 is the integral from minus pi over 3 up to pi over 3 of sine squared t dt. What's an antiderivative of sine squared t? Sine squared t doesn't have an easy antiderivative for us. So here's where our trig formulas are useful. 1 minus cosine 2t over 2, integrated from minus pi over 3 to pi over 3. I should really look that up and make sure. If I remember correctly, though, our book does not have the trig formulas in a nice place. That's why I made that for you. Hang on a second. All right, I double-checked myself because I didn't have that one as strongly in my memory from trig last semester, but it is correct. So now we can write this as the integral from minus pi over 3 to pi over 3 of 1/2 minus 1/2 cosine 2t dt. Just a little easier like that, because then an antiderivative of 1/2 is 1/2 t, and an antiderivative of cosine 2t is going to be 1/2 sine 2t, so that'll be minus 1/4 sine 2t. We need to evaluate that from negative pi over 3 to pi over 3. So we get 1/2 pi over 3 minus 1/4. Sine of pi over 3 is root 3 over 2. That's the tall one. Oh, sorry, it's 2 pi over, 2 pi over 3 is still root 3 over 2. And then minus 1/2 pi over 3, negative pi over 3, minus 1/4, and sine of negative 2 pi over 3 is going to be negative root 3 over 2. So what this is going to do is it's actually going to negate this sign. These can be pluses, and then that can be a plus. And I actually get a doubling effect. I think we're going to talk about that in a future section, so I won't make too big of a deal out of that. But I get 2 pi over 6, so pi over 3, and then minus root 3 over 4. And that's the answer. So I would strongly encourage you to practice your antiderivatives and your definite integrals by doing all of the problems in 339. If you have any questions, definitely ask me by email, or we can set up a Zoom meeting or something like that. Good luck with this one, guys. It's I don't know. it's hard to pick out a section that's like the most important, but this one kind of has put together so much of what we've done in the class so far.